So we need to think back to our Chapter 4 electron configuration chapter about electron energies and electron orbitals. So on the first energy level, right, energy level 1, n equals 1, what shape of orbitals could we have? You remember? Just S, right? If we get to energy level 2, what can we have? S and P. And we get to level 3, we could have S, P, and D. And then 4 and below can have S, P, D, and F. Okay, so what's happening here is that we have a now combination of these two energy levels to form something new. So when atoms bond, they kind of smush their electron orbitals together to make something new, a hybrid orbital. That's what we're looking at. Okay, so we're going to walk through what this might look like. CH4, let's find its molecular geometry. Molecular geometry, okay, CH4, right, its Lewis structure looks like this, right, real simple. Okay, which means it's electron geometry. You might want that sheet out as well. I think that's the back of your Pauling scale. 4 domains, right? How many lone pairs? 0 lone pairs, which means it's tetrahedral. Okay, so we're going to be able to use the molecular geometry of the central atom to help us define what type of electron orbitals now surround that. What shape are our new orbitals, okay? So it has 4 equal electron orbitals, right? We say when it's CH4, right, we've got an H here, an H here, an H coming out at us here, and an H going backward. Right, that's three-dimensionally what it looks like. Do you remember looking at a tetrahedral molecule? Right, kind of makes a triangle on the bottom and it's got one up top. So each of those electron orbitals have equal energy, right? They're all equal distance apart, 109.5 degrees apart. And they all have equal energies. So how could that be, right? How can they be stored in equal energies? Okay, so the way is that we have our electron orbitals are combining to form these hybrid orbitals. Okay, so carbon has 4 valence electrons that it is contributing, right? Would you agree with that part? Carbon has 4 valence electrons. And in carbon's outer shell, 2 of those electrons come from the s orbital, and 2 of them are found in the p orbitals. Would you agree with that? If we look at where carbon is located, 2 of its outer shell electrons are found in the s orbitals, and 2 of them are found in the p orbitals. Okay. S and p orbitals, we know, typically have different shapes. S orbitals are shaped like a circle or a sphere, right? They're spherical. And a p orbital is shaped usually like a, do you remember? Yeah, kind of like an infinity, right? A dumbbell type shape. Okay? So since we're making this new shape, we're combining them into basically a new one kind of, I want to say dimensional, but that's not really the word I want to use. One new shape that can take up all 4 of those bonds, right? Where all of those electrons can be stored. Not 2 of them in the s orbital and 2 in the p orbital anymore, but rather something that's equal for all 4 of those hydrogen bonds. Okay? So we're going to make new hybrid bonds, and we call these sp3 orbitals. And I'm going to walk through how they get that name. Okay, so that's not something you need to understand at this point. But what you can think about is now 2 s orbitals and 2 p orbitals are smushing together, right, to make a new electron pocket, right, an electron storage pocket. Okay, so that's essentially what orbitals are. Okay, and I'll walk through how we get this name, because that's a little bit tricky for us to see where that maybe came from. Okay. Okay, this would be a table I'd want you to look at. These are the most popular shapes, for each type of, yeah, I would write this. These are the most popular shapes, but maybe not necessarily all of them. I might have left off some that are on your sheet, but those are the most popular shapes going with that hybridization. And then I'm going to walk through kind of a pattern to help us determine that. Okay, but I want you to get it written down first, and then we'll talk through it. Of domains and the hybridization. Okay, all we're doing is counting out our electron orbitals, right, and we're putting them together. So when we have 1 domain, it can only be in an s orbital. When we have 2 domains, we have an s and one p orbital that have combined, right? When we have 3 domains, we've got the s orbital and 2 p domains that have combined, right? Are we on the same page? Or two p orbitals that have combined. Once we get to 4, there's 3 possible p orbitals and the s orbital that have combined, okay? There's only 3 possible p orbitals, because the p block can hold how many total electrons? 6, and each p orbital can hold 2. So that means there's only 3 possible. So we go s to sp3 to sp3. Now we add a d orbital. So all you're doing is counting the total number of domains, and then it goes s, sp, sp2, sp3, sp3d, sp3d2, right? And we stop there. So that's all we're doing when we think about hybridization is we look at the total number of domains. That means it could include lone pairs or not. Those are both bonding and non-bonding domains. So I don't know if you want to put that here, but these could be bonding or non-bonding. Right? And you'll see like in the 4 number of domains, it only lists tetrahedral and trigonal pyramid. It could also be bent, right? Those are just the most popular versions for that domain. Okay, so you can follow this sheet more clearly than your table, but you see when we get to 5 domains, there's really 4 possible shapes that would all be in sp3d shaped orbitals. Okay, so 4 total, which means it's an sp3 hybridization. So that means that around the central atom, around nitrogen, right, this domain, this domain, this domain, and this domain all have a new shape, which you don't need to be really concerned with about the shape. All have a new shape and a new energy level in which they're all equal energy. Okay, because they each contain 2 electrons, right, they're of all equal energy. Okay, and the molecular geometry for this would be trigonal pyramid. Okay, or pyramidal. Okay, so I'm going to have you try a few here on your own, finding the molecular geometry and the hybridization. Okay, so when we give our final answer, we call it an sp3 hybridization. Okay, give the molecular geometry and identify the hybridization. Okay, so SO2 Ci4, that's Ci4, not Cl4, and then this one is BCl3. There's no difference between an L and an I in this font for some reason. Okay. I'll rewrite them somewhere. Okay, so those are your 3. I want you to find the molecular geometry and the hybridization. So you got to draw the Lewis structure first. Okay. For SO2, there's a few possible structures here. You could have gone with a resonance in which it had a single bond on one side, double bond on the other, or you could have gone here, double bonds, and a lone pair on sulfur, which would give you expanded octet. So we could have a couple different answers here. But realistically, it wouldn't have changed the hybridization because you still would have had 3 total domains. Right? Would you agree? Yeah. So 3 total domains, 2 of which are bonding, and 1 of which is non-bonding, gives us what shape? Bent. Okay, so this is bent. And what hybridization do we have for those 3 orbitals? sp2. That's right. Okay, because we have 3 total domains. 1, 2, 3. So we have an s and 2 p orbitals that have been smushed together to form sp2. Okay, Ci4 should have been pretty simple, right? We complete the octets around each of these iodines, and we get a tetrahedral geometry. Nothing extra, right? What hybridization is tetrahedral? sp3. Our last one is BCl3. What molecular geometry do we have here? Trigonal planar. Are we okay with boron having an incomplete octet? Yes. Ethan, what did you have for your hybridization here? For BCl3? sp2. Good. So we see that even though they have different shapes, right, they can still have the same hybridization. They still have the same new electron orbital shape. Okay, very good. Questions about those? Intermolecular forces. And you'll see me abbreviate these IM forces a lot. Okay, intermolecular forces. There's a difference between inter and intra. Okay, inter means between two things. Intra means within something. So intermolecular forces means these are forces of attraction between molecules, not within molecules. Okay, so these are between two different molecules. Think about, but before we start looking at our different types of intermolecular forces, I want you to think about the transition of state between solid and liquid, which is called melting. Right? What happens when something melts? It goes from a solid to a liquid, okay. But what has to happen in order for something to melt? Heat. Has to have heat, right? The temperature has to go up. So what does heat do to a compound to make it to start to melt?
It heats it up.
Okay, but why does it start to melt? Okay, it starts. That's right. They start moving faster, and when things have more energy, right, it starts to break the bonds between molecules, which allows them to separate. Right? They can go from the lattice. Remember that crystal lattice we talked about in an ionic compound? That crystal lattice holds things in place. So it can go from that crystal lattice, and it starts breaking down those bonds. So they have to start separating, and the crystal lattice gets smaller and smaller, right? Until eventually we've got individualized molecules. Okay. So when we melt something, the particles are held together by something, these intermolecular forces. And when we add heat in the form of energy in the form of heat, we can start breaking down these bonds. So I want you to think about the process of a change of state as more than just, oh yeah, it's getting hotter so it melts, right? We need to be thinking about the fact that energy is being added, which increases the speed of the molecules, which increases their energy, right, which breaks bonds, okay? Okay, so if we think about the reverse side of that, if something has a really high melting point or a really high boiling point, that means that it has really strong intermolecular forces. Right, really strong intermolecular forces. Okay, so turn to page 204, and we're going to look at some values of boiling points of different compounds. Okay, so look at the boiling points on page 204. It's talking about at regular atmospheric pressure and all that kind of stuff. We're looking at the temperature of it in Celsius. Okay, non-polar covalent bonds are the weakest bonds that we have. Right, non-polar covalent bonds are weak. Electrons are shared evenly. And they're in covalent molecules. Remember, we talked about how covalent molecules have weaker intermolecular forces than ionics because most of them are gases at room temperature. I mean, it doesn't take a whole lot of energy to make them boil. Okay? So if we look at polar covalent bonds, the boiling points get a little bit higher, a little bit higher. If we look at ionic bonds, boiling point of salt is 1,413 degrees Celsius. Right, so to boil pure salt, right, you'd have to get it up that high. If you get to metallic bonds, the boiling point of W, which is tungsten, good, tungsten, one of our strongest metals, is 5,660 degrees. So hydrogen gas boils at negative 253, right, really close to absolute zero. Absolute zero is negative 273, okay. Oxygen gas boils at negative 183, yet our metallic bonds, or metals in general, don't boil until 5,000 degrees Celsius. So you see really difference between intermolecular bonds between covalent molecules and metals or even ionic compounds. Okay, water fits in. Do you see that in the polar covalent? Right at 100 degrees Celsius. Okay, so it kind of sits right in the middle there. Okay, a first type of intermolecular force that we're going to look at is called hydrogen bonding. Okay, when we say hydrogen bonds, it's a little misleading because it's not actually a bond. It's more of just an attraction. Okay. Okay, so hydrogen bonds exist between the hydrogen of one molecule and a partially charged atom of another molecule. Okay, and so when we say bonds, we don't really mean a true bond. It's an attraction, and it's a really strong attraction, but it's not a true bond, right? There's no trading of electrons or sharing of electrons, which would constitute a bond. But a hydrogen bond is a really strong attraction, and we demonstrate hydrogen bonds most often in water, okay? But hydrogen bonds, what charge will hydrogen usually kind of mostly carry with it or be associated with hydrogen? Usually a positive, right? So if it's going to be attracted to the oxygen of another molecule, what kind of charge or partial charge does oxygen need to carry with it? Right? Some kind of a negative charge. Okay, and it doesn't have to just be oxygen. It can be any partially negatively charged molecule or atom in another molecule, right? But a hydrogen bond is really strong attraction between a hydrogen of one molecule and a charged particle, a negatively charged particle on another. Okay, it's not really a bond. So I don't know why or who decided to name it a hydrogen bond when it's not really a bond, but I didn't make the rules. Okay, so it's not really a type of bond, but it is a really strong attraction. Okay, usually when they draw hydrogen bonds, or if you see dotted lines, you'll know that's a hydrogen bond. Okay, it's indicated as to these two things are attracted to each other, yet it's not really a true full bond yet. These hydrogen bonds are so strong that they usually make hydrogen-containing molecules have a much higher boiling point, right? With the exception of hydrogen gas. We see most hydrogen-containing molecules have higher boiling points due to this phenomenon of hydrogen bonding. Okay. And it usually is more in polar molecules, which we're going to look at here in a second. Sorry. These are the weakest type of intermolecular forces, and they're called London dispersion forces. Okay, and these are intermolecular attractions resulting from the constant motion of electrons and the creation of what we call instantaneous dipoles. And I'll show you what a dipole is. Okay, so in general, we're going to dive into dipoles here in a little bit, but in general, if I've got two molecules, okay, or two atoms in a molecule, A and B, okay, and B is much more electronegative. Let's say B is much more electronegative. Where would the electrons in this bond gravitate toward? Right? The electrons are going to slide toward B. Would you agree? If B is much more electronegative, right? That would create what we call a dipole in this molecule, right? This being the positive end and this being the negative end. Would you agree? Okay, the electrons are pulled a little bit more toward this side. This would create what we consider a dipole. So let's say it happens in another molecule right nearby. Okay, here's a negative charge, and here's a positive charge. Okay, this little attraction right here between this positive and this negative would be what we call a London dispersion force. Okay, or this intermolecular force. But since our molecules are in such constant motion and random motion, right, this guy is going to be moving away pretty soon, right? So that bond will break. They are not strong at all. London dispersion forces are very weak. So they'll hold them there for a millisecond, but if this guy wants to move on, like he will, right? It will move on. It's not a strong enough bond to hold it in place. Whereas hydrogen bonds are strong enough to hold those in place, right? Water has really, really high surface tension. You know what surface tension is? Right, how it kind of bubbles over sometimes, it has the true meniscus, things like that. It has surface tension sometimes due to these hydrogen bonds as well. Okay, but London dispersion forces act between all other atoms, but it's just such a small force, okay? So they're very weak attractions and they only occur for short periods of time. They act between all atoms and molecules, so it's not just the hydrogens, right? Hydrogens cause hydrogen bonding. But London dispersion forces act between all atoms and all molecules. Okay, so they're constant in everything. So they're the only forces that act between nonpolar molecules and noble gas atoms. Okay, so the only forces that keep noble gases together, right, as much as they're together, are these London dispersion forces. So they're really weak. Because the gas particles, as you know, don't stay together very often or for very long. Of intermolecular forces, hydrogen bonding is the strongest type. London dispersion are the weakest. Okay, that's something that you need to know. Which one is which? Okay. Okay, so now we're going to review polarity. These are our last kind of 3 topics of Chapter 6, hybridization, intermolecular forces, and polarity. And we talked about bond polarity, but now we're talking about polarity of an entire molecule. Okay? So a bond is considered polar. You should have this in your notes already, or you should remember this, when the electrons are shared unevenly between 2 atoms. Right? When we have uneven distribution of electrons, that gives us a polar bond. Okay, is that ringing bells, hopefully? Okay, uneven distribution of electrons means polar bond. So now we're going to look at when is a molecule considered polar. Okay, you can have whole molecules that are considered polar or nonpolar. Okay, for a molecule to be considered polar, it has to have what we call a dipole moment, right? Which is not this big dramatic thing that it sounds like. Okay, a dipole moment is when electrons are shared unevenly throughout the whole molecule, not just the individual bonds. Okay, and we're going to draw a few here and see what they look like. But a really good clue for a polar molecule is that if it has asymmetry. Okay, that's a really good clue for if a molecule is polar. Is it asymmetrical? In which case, yes, most of the time it's going to be a polar molecule. Okay, so could a molecule have polar bonds but be nonpolar as a whole? Yes, the answer is yes, right? You could have polar bonds but be nonpolar, and I'm going to show you how we determine that. Okay, we're going to look at HCl here for our first example. Okay, what's HCl named? Hydrochloric acid, good. Hydrochloric acid. So the Lewis structure for HCl is really simple, right? Okay, so if we look at our bond, we have one bond here in our hydrochloric acid. Which of these is more electronegative? Chlorine, right? If you take a look at your Pauling scale, chlorine is much more electronegative, a 3.0 to 2.20. Okay, so much more electronegative. Okay, and if you really broke it down into bonds, right, in your scale, that would be enough to form a polar covalent bond. Okay, but for right now, we're not worried about that. Okay, what we're going to do to indicate that this bond is polar, so we're going to draw an arrow. And that arrow gets drawn in the direction that the electrons would go. So between these two atoms, which direction are the electrons getting pulled? Toward which one? Chlorine, right? Chlorine is more electronegative, so that arrow is going to go to the left. So this little tail I put on the end, right, this telling us that this is the positive side, right, and the arrow goes to the negative side.
So why?
Because chlorine is more electronegative, those electrons are going to pull toward chlorine. So this arrow is showing us, this is called a polarity arrow, right? Something polarity. It's showing us the electrons are going this way.
So if it has more electrons, then it's more electronegative.
Well, no, this scale right here. You remember this guy?
Oh, yeah.
This number's bigger, so it's more electronegative than hydrogen. So the electrons are going to be pulled that way. Okay? Yeah. This is the only bond in our molecule, so that means this molecule, not only the bond, the molecule itself is polar, right? This is its dipole moment, right here, this arrow. Okay, that's what it's called, its dipole moment. It's gravitating toward chlorine here. Okay? Let's try another one. Let's try water. Okay, and we want to try to draw water in the correct molecular geometry. We know water has to be bent, right? So here it becomes a little more important that we start drawing them in the molecular geometry that we want. Okay, it doesn't have to necessarily be three-dimensional, but we need to start drawing them in the correct molecular geometry, right? We know water is going to be bent, so we want to try to draw it that way rather than putting lone pairs on either side, because that can kind of skew our view just a little bit. Okay? So let's look at each individual bond. Between oxygen and hydrogen, which is more electronegative? Oxygen. So I'm going to draw little mini polarity arrows, right? The electrons in this bond would gravitate toward oxygen. The same thing goes for the other bond, right? So here's my little minis, telling me with each of those bonds, oxygen is pulling those electrons closer to it. Okay? So now when we look at the whole molecule has a dipole moment that points us in what direction? Like that. This is our dipole moment, right? Both of those arrows are pointing toward the top of that molecule. That's where all of our electrons are located. So your overall dipole moment can go over the top of your molecule like that, and it needs to point to where the majority of our electrons are located. Right? Where are our electrons being pulled toward? So in this molecule that's bent, we've got two lone pairs on top, and we've got the electrons in the bond that are pulling toward oxygen. So overall, all those electrons are pointing in the upward direction. Does that kind of make sense? I know polarity seems a little bit new and a little bit abstract, but that's what we would be looking for as our dipole moment. Right? These guys are just telling us individual bonds, not as important. The big one is what we want, that dipole moment. Okay? Okay, sorry. All right, we're going to watch a little bit of a video here to help us with polar and nonpolar. Just a few minutes, so I'll get that pulled up. Okay, so NH3 has what molecular geometry? Trigonal pyramid. Right? And within these bonds, between nitrogen and hydrogen, which is more electronegative? Nitrogen, by a lot or a little? A lot, right? Kind of a lot. So we're going to go here to here. Right? And all of those are on the base of our molecule, right? And we've got this lone pair that's pulling it up to make it a pyramid shaped. So our dipole moment should go toward where? Go toward the lone pair, right? Because we have that triangle base of hydrogens, right? All the nitrogens are pulling those electrons up, plus we've got a lone pair on the top, right? It's going to lead us to believe that it's polar. And so that dipole moment just needs to go toward that lone pair. Okay? I'm going to tell you almost 90% of the time the central atom has a lone pair, it's going to be polar. Okay, so that's a good indicator to us that we're going to have a polar molecule. If we've got a lone pair, it's going to be polar. That's not the case 100% of the time, but most of the time it is. So if we've got a lone pair on our molecule, on our central atom, most of the time going to be polar there. Okay? What about CCl4? Polar or non-polar? Non-polar, right? Right. It's symmetrical. They're all made up of the same atoms on the outside. So even if they're playing tug of war with those electrons, it's even around the whole molecule. So within the bonds, chlorine is more electronegative, right? So we'd go here, 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 and here, right? But their tug of war is equal, right? So this would be non-polar. Okay. And if we ever get into a situation where we would want to look at, like, let's say, NaCl, right? This electronegativity is so dramatic that really we have a negative and a positive. This is an ionic, right? It's not a polar bond or a polar molecule anymore. This is an ionic molecule because it's a metal and a non-metal, which has taken the electrons so far as to break them up into formal charges. So they're not partial positives and partial negatives anymore. It's a full negative charge and a full positive charge. Okay, so you need to make sure and identify if it's a metal and a non-metal, it's not necessarily a polar bond, but it's a ionic. Okay, once they get that far apart.